Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at igneous rocks. So this video is going to correspond to section 5.7 of your textbook. So now we're going to move on to thinking about why magma actually wants to move through the crust, because this is actually quite an important question. Once you've generated the magma, why does it actually go to a new location? Why doesn't it just simply stay where it was generated? So to begin with, let's think about what magma actually consists of. Well, magma actually consists of three separate parts. The first part is the liquid portion of your magma, which is referred to as the melt. And this is of course being created through the melting of minerals, either due to heating, decompression, or the addition of a flux, something like water. Now, the next portion of your magma can be solid phases. This could be solid crystals of a silicate mineral that have formed as the magma's been cooling during its journey, or it could even be pieces of the host rock that have fallen into the magma and are simply being swept along with it. The final component of your magma is going to be the gaseous components, which we refer to as volatiles, and these will be dissolved within the magma itself. Now, the most common volatile in magma is simply going to be water vapor. That's then going to be followed by carbon dioxide and then normally sulfur dioxide. So these are the big three volatile phases. Now, in terms of the magma itself, the vast majority of your magma as it's moving through the crust is going to be the melt phase, with the solids and the volatiles being a lesser component, but nevertheless important. So let's think about what actually constrains how far a magma can rise through the crust. So what's actually going to help or hinder the magma movement? So the first thing that's going to help or hinder the magma movement is magma pressure. So magma pressure is simply the result of the weight of the rock which surrounds the magma. So think of it like a tube of toothpaste. If you have a tube of toothpaste and you squeeze it gently, a little bit of toothpaste comes out. If you have a tube of toothpaste and you squeeze it hard, a lot of toothpaste comes out. So typically, the higher the pressure put on the magma by the rocks that surround it, the greater the magma pressure will be, and therefore the magma is going to want to flow out of that area towards a region of lower pressure. Now, the higher pressure also makes it easier for the magma to move, because that pressure means that the magma can more easily force open cracks to allow itself to escape that region. Now, typically, most magmas will be under pressure, and the deeper your magma is, the more pressure it will be under, because there's more rock above it pushing down. So this means that as your magma moves closer to the surface, the magma pressure will typically begin to decrease as the thickness of rock above the magma is getting thinner and thinner. And this means that magma pressure is not a constant, it's typically higher towards the base of the crust, and as you move up through the crust, magma pressure will typically decrease. So the next constraint on how far a magma is going to move is its density. So normally magma is less dense than the rock which it is passing through. That goes for most situations. So in a lot of cases, the magma being less dense, it will naturally want to rise, and that's exactly what it will do. It will go through the crust. Now, eventually, there are situations where your magma can reach a point where its density is either equal to, or maybe in some cases greater than, the rock that it's passing through. And in this situation, your magma is going to naturally stop rising, and it's going to settle out at that location, and it's going to form something like an intrusion, or maybe another feature, something like a sill. So as long as the density of your magma is lower than the surrounding rock, it's going to want to rise. As soon as the density becomes equal to the material that it's passing through, it's going to slow down and stop. The next variable is gas pressure. So we've discussed that one of the three things that makes up your magma are volatile phases. Now, these volatile phases are dissolved in the magma as long as the pressure is high. Once again, think of that bottle of Coke. When the Coke is unopened, there is a lot of pressure inside the bottle, and that high pressure inside the bottle stops the carbon dioxide from leaving the liquid. As soon as you break the seal on the bottle, the pressure inside the bottle drops, and the carbon dioxide can exit the liquid in the form of gas bubbles. And it's exactly the same process with magmas. As your magma starts rising towards the surface, the pressure is going to drop, and eventually the pressure is going to get so low that the volatiles are going to start exiting the magma, forming bubbles. Well, as soon as you start forming these bubbles, it's going to cause the density of your magma to decrease. And as we've already discussed, the lower the density, the more efficiently your magma will rise. So by adding this the addition of these gas bubbles to your magma, it's going to help the density of your magma to get lower, and it's going to want to keep going up. The final factor that's going to help or hinder the passage of magma is stress. And we're talking about tectonic stresses here, produced by plate tectonic processes. So things like mountain building, for instance. So these processes can be quite helpful because they can sometimes open up a lot of cracks, a lot of joints, a lot of faults through which magma can very easily move. So the application of a tectonic stress to an area can be positive for magma movement. At the same time, stresses can also sometimes be negative. If the tectonic stress is very, very strong, it can actually force pathways closed and therefore stop the magma from moving. So stresses are a bit of a double-edged sword. Sometimes they can be helpful, sometimes they can hinder the path of your magma. So these are the factors which are going to help to constrain, how far and also how fast your magma will rise. So now we've discussed the factors which control how efficiently or inefficiently a magma can move through the crust. We now need to think about what factors are going to control how easily a magma can move by itself. And the primary factor is going to be the magma's viscosity. So viscosity is a measure of a material's resistance to flow. So a high viscosity liquid is going to flow very slowly. Think of something like cold molasses. In contrast, a low viscosity fluid is going to flow very easily. Think of something like water. So clearly viscosity is going to control the movement of your magma. Low viscosity magmas are going to flow very, very easily over a wide area or move through the crust very, very easily, whereas high viscosity liquids are not going to be able to flow very, very far, and they're going to have more difficulty moving through the crust because they're essentially stickier, for want of a better way of describing it. So what are the factors that control viscosity when it comes to magmas? So the first factor is the most straightforward one, temperature. Typically, the higher the temperature, the lower the viscosity. So this means that lower temperature magmas, like felsic magmas, will typically have a higher viscosity than magmas which are formed at a higher temperature, like a mafic magma, which will typically have a lower viscosity. So the higher the temperature of your magma, typically the lower the viscosity, and therefore the more easily it will flow. The next constraint is composition. Most importantly, how much silica is there in your magma? So you're thinking, well, how does the silica content actually affect how easily a magma flows? Well, when you think about silica, you think of those silica tetrahedrons. Now, those are going to all join together to form chains in your magma. Now, these chains of silica tetrahedrons will be more numerous and longer the more silica you have in your magma. And the more numerous the chains are and the longer the chains are, the more likely these chains are to interact with each other, to wrap around each other, for want of a better way of describing it. And so this is actually going to help to affect the viscosity of your liquid, because the more of these silica chains you have, the stickier your magma will be. Or to put it another way, the more of these chains you have, the higher the viscosity of your magma will be, because these chains are all interacting with each other, they're all locking into each other, wrapping around each other, and it helps to slow down the flow. So this means that magmas that have a very, very high silica content, so something like a felsic magma, is naturally going to have lots of these chains, and they're going to be quite long, and this is going to mean they're going to interact with each other, and they're going to help to slow down the flow. They're going to increase the liquid's viscosity. In contrast, a mafic magma has a lower silica content, therefore the chains are less numerous, they are also going to be smaller, and so this means they are a bit less likely to interact with each other, and so this means the magma is going to have a lower viscosity, it's going to be less sticky. So the final factor that affects how easily a magma moves is the percentage of crystals. Typically, the more crystals you have, the more obstructions that will cause, and therefore the more difficult it is for your liquid to flow. So this also comes back to temperature to some degree. Typically higher temperature magmas will often have a temperature which is above the temperature at which crystals start forming, so they will often have relatively few crystals in them, and so that means once again they can flow more easily. In contrast, a lower temperature magma, something like a felsic magma, will typically have a magma temperature at which crystals can start forming, so you're going to have a higher percentage of crystals in your magma, and so this is going to make it more difficult for your magma to flow. So these are the three factors which are going to affect how easily our magma will flow, and obviously therefore that's going to be directly reflected in its viscosity. So what does that actually mean in terms of magmas moving through the crust and magmas being erupted onto the surface of the Earth? Well, when a high viscosity magma, so that's one that has typically a lower temperature, a higher silica content, and quite a high proportion of crystals in the magma, well, when that kind of magma is erupted onto the surface of the Earth, it's going to have quite a high viscosity, and so it can't flow very far from the volcanic vent. And so this means your lava will start to pile up very, very close to your volcanic vent. This typically means that your volcano will not be very wide, but it will be quite high. In contrast, when we have a lower viscosity lava, something like a mafic lava, which is typically quite a high temperature, it has fewer silica chains, and it has a much smaller proportion of crystals as part of the magma, well, these magmas will be able to flow very, very easily. And so this means that these magmas will extend laterally quite a long way from the volcanic vent. So this means you end up with volcanoes which are very, very broad, but not very high, because the lava isn't piling up, by the vent. Instead, it's spreading out over a wider area. So you can see how the viscosity of your magma is directly affecting the morphology of the volcanoes that form. So as we've discussed, these higher viscosity magmas are typically going to have a lower temperature, more abundant silica chains, and also more crystals in the magma as well. This is going to help slow down its flow. It's also going to mean that it's more difficult for the magma to flow to the surface. So this is going to reduce the speed at which magma can move from the chamber and eventually be erupted onto the surface of the Earth. In contrast, our lower viscosity magmas are typically going to have a higher temperature, fewer silica chains, and fewer crystals in the magma. This obviously means the viscosity is going to be lower, and so this will mean that the magma can also rise through the crust more efficiently, and it also means therefore that when it erupts onto the surface, it will spread laterally. Okay, thank you for watching everybody, and have a good day.